Hello, and welcome to the next installation of Algebra 2. So we are skipping straight to Section 8, or Module 8, all about exponential growth and decay. So we're skipping Module 7 because I personally think that exponential growth and decay is very important, especially in today's COVID era. So instead of going over their little Spark Your Learning, we're going to do a little COVID lesson. So remember at the beginning of this whole thing, there's this big thing about flatten the curve. Flatten the curve, flatten the curve, flatten the curve. So what are they talking about? So I'm using their square, and we're going to make ourselves a little graph. And let's call the x-axis, let's see here, what do we want to say? We're going to say that this is time in weeks. So like this would be the first week, the second week, the third week, so on and so forth. So then our y-axis is going to be number of cases. So this is kind of what they were talking about when they were saying flatten the curve, or what epidemiologists or people who study diseases were so concerned about. So let's say we're going to say that our y-axis is in hundreds. Okay, so this would be 100, 200, 300, and so on and so forth. So let's say COVID first happens, right? And we're going to call that week 1. So week 1, let's say there's 100 cases. Okay, so we've got our data point right there. We'll even switch to a different color. So week 1, we've got 100 cases. So the problem is that week 2, they then measured 200 cases. Okay, so, what's the problem? It's just a line, right? Just a normal line, something we'd expect. Well, the issue with diseases is that the more people you have diseased, the more likely you're going to spread the disease. So the more people get sick, the more people get sick. So we're going to make our little chart, 7, 8, 9, 10. So a straight line would have been okay. We can deal with the straight line. But the issue is that this first week and between the second week, the cases doubled. The cases doubled. Why is that important? Because now we're at 200. So what is our week 3? It's not going to be 300, it's going to be 400. Because the cases were doubling. Okay? So then let's go to, so that was week 3. I know my graph's a little janky, but, so week 4, so what's double 400? So now we're at 800. And then week 5, we're going to be at 8, 9, 10, 11, 12, 13, 14, 15, 16. It's going to be all the way up here. So this is an example of an exponential growth curve. So this is what disease scientists were afraid of when they first saw these numbers. Now remember, the data is much better now, and we have better treatments, but in the beginning, it was like anywhere from like a 1 to 3 mortality rate, 1 to 3% mortality rate. So that means that like at some points, 3% of people that got it would pass away. So if you can imagine, this exponential curve became dangerous because let's say you get 1 million people that have it, that's 3% of 1 million, that's a lot of people. So this exponential curve is what they're talking about, flattening the curve. So that was part of the initial shutdown. So that was our worst case scenario. What we wanted to happen, let's say so by the time we were flattening the curve, it was probably week 2 or 3. What they wanted to happen was for the numbers to start to go down so that our hospitals could deal with the sick people and kind of get them out the door so to make more room for other people. So this is what they were talking about, flattening the curve. This curve is a little bit more flatter. So that was all exponential curves. This blue curve right there is an exponential curve, and that's what we were so concerned about, especially in the pre-days of COVID, because those numbers were very much like that, because we were measuring like every so often the cases would double. So let's learn more about exponential curves. So the example that we used in the introduction was an example of an exponential growth function. So right there, you can also have an exponential decay. And so both of those, one of them is growing, the other one is decaying or getting smaller. So what that looks like in algebra terms is you're going to have an f of x equals b to the power of x. So your variable is going to be in your exponent. Up until now, we haven't really dealt with that type of function just yet, but here we go. So our b, this is just typically going to be any number. We're going to start with using 2 over and over again, but you can also have an exponential decay. So if this number is less than 1 and greater than 0, so basically a fraction, it's like 1/2, then you're going to have an exponential decay. So if you think about f of x equals like 1/2 to the power of x, whatever x is, you're basically dividing the number in half that many times. So that's going to get smaller and smaller and smaller, whereas if b is greater than 1, it's going to get bigger and bigger and bigger. And b does not equal 1 because that would just give us a straight line going across. It would not give us an exponential growth function. So as the value of x increases for our f of x, so think about as x gets bigger and bigger and bigger, f of x is going to increase. As the value of x increases for the value of g of x, again, let's say x is 100, you're just going to divide by 2 100 times. It's going to get smaller and smaller and smaller. So it's going to decrease. So some general characteristics there. And then here we've got a chart. I'm just going to get the answers real quick. These are not it. I wonder if they're going to show us or if I'm going to have to do it all in front of you. Oh, look, I got one right. That's funny. Okay, so I'm going to have to do it the old-fashioned way. So as we go through these, I'm not going to do them all, but so as x equals -2, f of x is going to be 2 to the power of -2. So that is the same as 1 over 2 squared. So that's where they got the 1/4 from. And then 1/2 to the power of -2. So that's going to be 1/2 power of -2 is equal to 2 squared, which is going to be 4, right? So same thing here. We've got -1, 1/2. So then -1, so that's going to be 2. 1 and 1. Yay. This one's going to be 2. So again, that's 2 to the first power. Let's see here. 2 to the second power is 4. 1/2 to the second power is going to be 1 divided by 4, or 1/4. And 3 is 8. So notice how it's doubling. Interesting. And then this is going to be 1 over 8. There. Look at that. I didn't even need a calculator for that. So notice how the pattern goes. Every number, this is doubling. And that's where this 2 comes from. Whereas here, every number, it's being cut in half. That's where this number comes from. So if we were to graph these things, this is probably very important to remember. Here is the exponential growth, and then the exponential decay. So notice how this part right here gets closer and closer and closer to 0. But if our g of x is equal to 1/2 x, so again, 1 is going to be 1/2. 2, you're going to take 1/2 divided by 2. 3, you're going to divide by 2. 4, you're going to divide by 2. 100, you're going to divide by 2, divide by 2, divide by 2. So on and so forth. You're still going to have a positive number. So this curve here, this is an exponential decay, gets closer and closer to 0, but never actually touches 0. And hopefully you remember that is called an asymptote. So a function is or has an asymptote if it gets closer and closer and closer, but never actually hits that number. So in both of these cases, you have an asymptote at y equals 0. So that's going to be important later on when we start exploring more characteristics of exponential growth functions or exponential decays. So if we're talking about our characteristics, these graphs are very helpful with that. So our domain, what values of x can we possibly shove in there? I'm going to say all values of x. So that's this guy right here. This reads values of x such that x is within the set of real numbers. That's what that capital R means. I think I've used that before, but that is math lingo for all real numbers. And I put it both places because, again, you can look at any x here and there is a value for it. So the range, though, that's going to be a little bit different. Look at our y values. Do we have any negative y values for these? And the answer is no, we don't. So y is such that y is greater than 0. And that's for both of them. So far, there's some similar characteristics here. Here's where we're going to change our end behavior. So our end behavior for our growth function is going to approach infinity. As x approaches infinity, y approaches 0. That's not it. As x approaches infinity, y approaches positive infinity. As x approaches negative infinity, y approaches 0. So notice how that arrow means that y approaches 0. It doesn't necessarily... Come on. Why aren't you... So it doesn't mean that it actually hits 0. It just means that it approaches 0. Why are we doing this? Okay, fine. We're still going to move on. So this one goes here for our exponential growth, and this one goes here for our exponential decay. So this is as x approaches infinity, y approaches 0, and as x approaches negative infinity, y approaches positive infinity. So again, as you look at here, as you go this way on our decay function, it gets bigger and bigger and bigger. Try it one more time. Whatever. So horizontal asymptote, we talked about that. It's going to be the same for each one. Y equals 0. And y-intercept. Y-intercept. Oh, I'm sorry. I thought it meant x-intercept. I was like, it doesn't cross the x-axis. So the y-intercept is this guy right here, and that is that x equals 0 or 0, 1. So here we got 0, 1, and 0, 1. Again, it's the same for both of them. Oh, they're not even going to let me check it because I can't get these. Whatever, technology is failing us. We're still going to learn math. So describe the similarities and differences. We kind of talked about that as we went along. Using the key characteristics from part C, what generalizations can you make about the general exponential function where b is any positive number other than 1? The function increases exponentially for b greater than 1 and decreases exponentially for b in between 0 and 1. So we've talked a little bit about the characteristics of exponential growth and decay, but we also need to talk about what you can do to that function. So just like we talked about in like module 1 or 2, whatever, you can move that function around using transformation type stuff. So let's transform exponential growth functions. So I hope this looks a little familiar. It does use the same letters as before, but notice the things like H, K, A, and B. So this is how we're going to move this function around, as well as either vertically compress or stretch the function. So these are all the parameters that we're going to be using. So the parent function is still our f of x equals b of x. That is our regular normal function. But we can move that based on the things that we do, and that you should be seeing a pattern here because it's the same as everything that we've learned previous. We're just now shoving it into an exponent as opposed to, the other functions that we've used. So if we look at our graph, we've got, let's see here, which one's our parent function? Looks like our red line here is more or less a parent function. So f of x equals b of x, in this case b equals 3. So then, you can do all kinds of stuff to it. You can vertically compress or stretch it with a number out front. So notice the blue is 2 times 3 to the power of x. Still has the same asymptote. Still is an exponential decay. But notice how it crosses the y-axis at a different point. That's going to be important later on. So if we want to transform it up, so we look at this guy, we just have a plus 4 on it. So that moved our asymptote here up 4 units. And then if we want to move it to the left or right, that's what we have, this part right there. So notice we've got our asymptote, and then we cross the y-axis at 2 above our asymptote. So we moved it up 4, so here's our asymptote, and then we moved it to the side, or to the right, 1, so then it crosses right here, 2 units above where the asymptote is. So this is all going to come into play later on, so that's why I bring it up. So consider the function shown in the graph, which is the parent function. We talked about f of x equals 3 of x. Compare the y-intercepts of the graph, so we did that. Compare f of 1 and g of 1, so we didn't really do that. So f of 1 is our parent function, so that's going to be 3 to the first power, which is 3. So that is 1, 3, right there. And then g of 1 It did say g of 1, right? Yeah. So then g of 1, g is right there. G of 1 is going to be equal to 6, right? So that's 3 to the power of 1, which is 3, times 2 is 6. So that's going to be 1, 6. And that's our blue line, remember. So again, it lines up, but that first number is different. So this is a more growthy, I don't know, it grows faster exponential curve. Let's ask me what that is. F of 1 equals 3, and g of 1 equals 6. So g of 1 is 2 times f of 1. I don't know what they're really looking for here. Try again. Let's see if I said put an x there. So g of 1 is there you go. So they're looking for twice. So compare steepness. Again, we've kind of already talked about it. Notice that the graph of f of x and g of x have the same horizontal asymptote. How is the horizontal asymptote of the graph of j of x related to the horizontal graph of g of x? So again, we've got our j of x up here in purple, and our f of x, and I mean really just all of the other ones. Down here they've got y equals 0 of an asymptote, and then the j of x, when you added that 4 outside of the function, it translated it, or it transformed this function up 4 units, the asymptote up 4 units. So what other characteristics do we need to go through? Notice that the graphs f of x have the same horizontal asymptote. Okay. The table shows the first, second reference points for the parent exponential function. For any base b, what facts explain why these are good reference points? Select all that apply. Any base raised to the 0 power is 0. That's false. Any base raised to the 0 power is 1. That's neat. Any base raised to the first power is itself. So these are going to be our reference points. We're going to end up using these later on to help graph or write an equation based on a graph. So you're going to need to know these reference points, and that's why we pick our reference points, because we can cancel out some of this stuff and it'll make it a little bit easier for us. So let's start using these parameters A, B, H, and K. Just like we've done in the past, it is helpful to use specific reference points when graphing these functions. So, oh good, my pencil is working. So you've got your parent function, you've got your first reference point at 0, 1, and then you've got your second reference point at -1. And so that can just make it really easy to figure out what b is for your parent function, and then from there you can either add the rest of this stuff, or if it's a parent function, then you're done. But usually it's not going to be. So we've got this guy, or it's the same thing as here, as your generic version of a function, as complicated as it can be. But this will help you figure out your k, your h, and your a, and then you have to use your parent function to figure out your b. So just like we did before, you're going to use certain points to figure out certain parts of this equation, and you will be able to eventually either graph or figure out the equation of a graph using those reference points. So let's see how this goes. So our first one says graph graph g of x equals all that stuff. So first thing they want us to do is identify the parent function, the base, and the parameters. So our parent function is 1/2 x, right? So our base is 1/2. So right there, our base is 1/2. And then from there, we can compare these two functions right there. Our a is going to be 2. Our minus h, so our h is going to be 4, because there's a minus 4 there. And then our k is -1, because normally it's plus k, but this time it's minus a number, so the k is negative. So we've got all these things written right down there. So from those parameters, we can then graph it. So let's see here. What transformations do these represent? So we've got a horizontal transformation, a vertical transformation, and a horizontal stretch or compression, whichever one it is. I get them those both confused. But if you use reference points, it doesn't matter. You get the same equation. So what else we got? Find the reference points and the asymptote for each function. So here's our parent function that we started with. Our first reference point is always going to be x equals 0, because it's easy to find. So when you raise anything to the 0th power, it is going to equal 1. So that's our first reference point. Our second reference point, again, if we look at this, if we say x equals -1, that's going to be pretty easy to figure out. So x equals -1, and that's going to make our f of x equal 2. And so our parent function, our asymptote, is always y equals 0. So now we need to use this kind of stuff to figure out our first reference point for our g of x. So right there. So let's see here. I would say if we pick x equals 4, so x equals 4 makes this go to 0. So then we're just going to have 2 minus 1 is 1. Our second reference point, this time we need something, on the negative side. Let's see here. So we did 4. So what if we did x equals 3? It's not on the negative side, but it's 2 reference points. So if we said x equals 3, then we have this 1/2 to the negative first power, which means it's just 2. So 2 times 2 is 4, minus 1 is 3. I have no idea if these are the reference points they were looking for, but we'll find out one way or the other. And so our asymptote is y equals -1. That comes from this guy right there. Y equals -1. That one I'm confident about. Hey, look at that. Woo! Well done. You didn't give up, and your effort paid off. So what I did there is I was looking at this part. Our first reference point is when this goes to 0. And our second reference point is when this goes to -1. Those are 2 points that are easy to find. and will help us graph our curve. So what is the image of the graph of G of the point 1, 1/2 of graph F? So on this graph, we have 1, 1/2, x equals 1, y equals 1/2. So then the image of that would be translated down 1 and some other stuff. So I'm kind of going through here, doing some math in my head, trying to figure out one, 1/2. So I want to say it's 5. And the reason I want to say that is because x equals 1, 1/2 on this one. This x is 1. So then as I was looking through here, when I plug 5 into this one, I'm going to get that 1 in the exponent, which is kind of what I was going for. And then I just didn't do the math for the y, but that's when I had multiple choice. So if we were to graph both of those functions, here's what they're going to look like. Our blue is our parent function. Notice here's our 2 reference points. And then the red is our new function. So it has moved over. Remember the asymptote was moved to y equals -1, which is why we can go into the negative side. And here are our 2 reference points. So remember this shape because this is how we're going to graph. You're going to have your 2 reference points, and then you're just going to kind of, just guesstimate based on the curve. You may have noticed that there's a bit of scenery change. Turns out I ran out of time at school, so here I am. So if you hear my kid, not my fault. So anyway, we have learned about exponential graphs. We have created a graph based on a function. Now we're going to try to create a function based on the given information in this graph. So we've got 2 of our reference points. We've got an asymptote, and so we should hopefully be able to figure out our function based on that information and using this little guy right here. So let's try it out, shall we? So first step, I want to go in their order because I would start with the asymptote, but that's just me. Hey, look, use the asymptote to identify k. The asymptote is at y equals 3. So there's our asymptote. And so our k, this number right there, we already know is k equals 3. So that means that our whole function has a plus 3 at the end of it because it's translated up 3 units. So there's our asymptote. And so k equals 3. So then we're going to use the first reference point to find k. First reference point and k to find a and h. So I was just looking at, at this part right there. So our first reference point is our -2, 4. So with our -2, 4, remember they showed us this. So our x component of our first number there is our h. So we know that h is -2. Then we know that our second part is a plus k. So we know that a plus k equals 4. Well, we know that k equals 3, so now we have a plus 3 equals 4, a equals 1. So now we know that k equals 3. What else do we know? H equals -2, and a equals 1. So if we come back up here to this guy, so we're almost there, right? All we need to do is figure out our base, which is our parent function, and then we should be able to put all the pieces together. So how do you know that a equals k? So you guys saw me do the algebra on the screen. So now we can use the second reference point, a and k, to find b. So again, here's our second reference point, and that reference point is going to equal 1 plus h. So, you know, we kind of already know that. Oops, I got rid of all my other ones. So we don't necessarily need that. We already know what h is. We can use that to check things. But the second part, we have a times b plus k is going to be equal to 5. So here we have ab plus k equals 5. So we plug in the things that we know. A is 1, so that's just going to be b plus 3 equals 5. So b is equal to 2. So our base, or our b, is 2. So now we can put it all together. So if we look up here to this guy, Molly wants to go downstairs. But we can put that function together. So we've got a equals 1, b is 2 to the power of x plus 2. So why is that plus 2? So we got minus h, and we have a negative number here. So minus a negative is a positive, so that's why that's going to be plus 2. And then outside of the exponent is going to be our k, which is 3. So our g of x is equal to that guy right there. So I'm sure that that's probably our next step. Let's see what we got here. So how are the values a, b, h, and k related to the graph? Let's look at the graph. So k is the asymptote. That's what I know. K equals 3 indicates a shift of the graph. So our graph went up. So let's see here. H is going to be our shift to the left or right. In this case, it's to the left. So h equals -2 indicates a shift of the graph of the parent function to the left. B is our base. B is for base. And then 1 indicates no vertical stretch of the parent function. I like it. So then we write the equation. They got the same thing we did. So life is good. So there we go. Hey, so let's end with a word problem. So as you all know, when you buy a vehicle, because you've all bought so many vehicles, I'm sure, as soon as you drive it off the lot, its value goes down. So we call that depreciation, and so that's kind of what this is talking about. So we can model depreciation with an exponential decay function, because if you think about it, the car is never really worth zero money. I mean, it's always at least worth scrap metal, right? So there's an asymptote of its lower cost. So An exponential growth or decay function has the form. So we've got our equation right here. A is greater than 0. R is a constant percent increase or decrease for each unit increase in time t. The base, 1 plus or minus r, is the growth or decay factor, and r is the growth or decay rate. So there's a lot of things they're giving us here. Basically, our growth and decay. R is the percent increase in decimal form. R is the percent decrease in decimal form. And then we've got our growth factor. So, Delia, I don't know how to say that name, paid $23,000 for a car. If its value decreases 11% per year, for what whole number of years will its value V remain above $6,000? So the way we're going to figure that out is we're going to write an equation using this stuff up here, and then we're basically going to equal that to our $6,000, and anything above that, we're good to go, which it starts above it. But when it equals $6,000, that's how many years it'll take for it to be above $6,000. Anyway, so let's write the model for the car's value. So our A is the initial value. So A is the initial value. That's right there. If its value decreases 11%, so let's see here. 11%. So we're looking at a decrease, so it's a rate of decay. So that's going to be 1 minus R, or R is 0.11 or 11%. So then we've got 0.89 left, and then raised to t. Okay. So the initial value of the model purchase price car was that, which corresponds to t equals 0. Yay. So t equals 0 just means the beginning of when she initially started it. None of this has happened yet. So when that t equals 0, that t takes this percentage and turns it into a solid 1, which does not change the 23,000. How do you determine the growth or decay factor? Match the steps to determine the growth or decay factor. So first, let's see here, write the decay rate, 11% as a decimal. Something I did in my head, but that is technically probably the first thing. But before that, so I just went through and read all of these. We should have probably determined whether the function is decaying or growing. Since the value is depreciating, the value is decaying. So that would be our first step. Our second step is write the decay rate as a decimal. And our third step is you plug it into the appropriate equation. Yay! Graph the model and answer the question. Love it! Graph the model. That makes it way easier, right? So you are going to stick this equation into your calculator. So I'll go ahead and show you how to do that. As a reminder, I'm going to write it on the screen. 0.89 t. So we're going to plot our handy dandy calculator. And here we go. So since we are graphing, we're going to use the y equals function. Clear out our other thing. So 23,000 parenthesis. You could also multiply. It wouldn't have mattered, but Now use the power button. And in this case, our t is just going to be an x for our graphing sake. And let's see what it looks like. So I can't see it. The reason that we can't see it, and I'm just looking at based on our characteristics that we learned. So that means that it is probably a much larger equation. So at, higher. So at x equals 0, this is at 23,000. My window is like 1 to 10. So I can either zoom out. I did push the zoom out button, right? I think I zoomed in. Zoom out. Zoom out. Zoom out. Oh, I think I saw it. Oh, there it is. Woo! Zoom out. No, let's zoom back in. All right, so this is kind of what we're looking at. And we need to know, I forgot, when the value is less than 6,000, right? So when v equals 6, so if we look at our graph, I mean, we can kind of use the trace function. Our y values are going to be the value of the car, and our x values are going to be time in years. Oh, I already passed it. That's what I get for not paying attention. Oh, no, I didn't. Did I? I'm missing a 0, aren't I? Yeah, I'm missing a 0. So I'm going to go over here, and I think if I just push 0, no. So notice how there's this blue INS button right above the delete button. So we're going to insert a 0. So now I've got my 3 zeros. No wonder that didn't make sense. So we can trace. So I'm looking at this number right here, and I'm looking for it to be about 6,000. So 9.6 is 7,000. 12 is 5,000. So it's either 11 or 12. So I'm going to come over here to our table. So second table. And let's see, can I enter my own? So I'm just scrolling down until I get 11 or 12. So again, think about the question that we're trying to answer. How many years will this car be above $6,000? So at 11 years, it's going to be slightly above $6,000. But after that, it's going down below that 6,000. So the answer is going to be 11 years. Unless they want us to round to something weird. So let's see what they got. Then identify the intersection point, which is approximately 11.5. Indicates that we'll use their 11.5 years, the value of the car will decrease to about 6,000. So the value of the car is above the whole for the whole number of 11 years. So notice how this is not a normal rounding number right here, because of the context of what we're talking about. Typically 11.5 we would round up, right? But in this context, if we rounded up to for 12 years, it would be below that 6,000. So that's why we did not do our normal rounding errors. So make sure you're thinking about everything and keeping the situation in context. So there you go, exponential growth. Try the check on learning out, and I'll see you there if you need it.